Swayam Prabha. Digital India. Educated India.
Hi friends, now we will discuss on the topic cleaner liquid fuel production from petroleum crude. In the previous class, we have discussed how to produce liquid fuel from petroleum crude, and now we will see how the liquid fuels can be produced more cleaner. Actually, we have come to know that the petroleum crude contains different types of impurities, like say salt content, sulfur, nitrogen, oxygen, etc. So, these impurities can create some problem, and during refining process these can also be transferred to the liquid fuels, and when the liquid fuels will be used as a transport fuel, at that time pollutions will come. So, we need some cleaning options, some methods to remove those pollutants from the liquid fuels. Secondly, we have come to know that the residual part, particularly the vacuum residue, contains high asphaltene, high sulfur, high metals, etc., and this part is of less interest to the refiners and poorly managed and creates lot of environmental problems. So, upgradation of this vacuum residue is required, and that can give us a cleaner route or cleaner option to the overall refining process, and it will also help to increase the economy of the refining process. Thirdly, we have come to know that gradually the petroleum crude quality is decreasing, its sulfur content is increasing, viscosity increasing, and degree API is reducing. So, the processing of this heavy crude through the conventional technology is not that effective, may not be that effective. So, we need some alternative technology to use this feedstock, heavy feedstocks for its refining. So, these are the topics or subtopic we can say we are going to discuss in this module, and in this class we will discuss basically on the impurities removal, and the contents are impurities and need of their removal, then process for impurities removal like sulfur compounds removal, and then sulfur, nitrogen and metal removal. So, sulfur can be removed by sweetening process, and all sulfur, nitrogen and metal can be removed by hydro treatment, and we will make some more discussion on this topic. So, as we have discussed that crude oil contains different types of impurities, salt and sulfur, nitrogen, oxygen, etc., and desalting process is used to remove the salt from the crude oil, but that salt which is dissolved in the emulsified water or in the crystalline form, and basically we have seen there sodium, calcium, magnesium chlorides are removed mostly. Apart from these, we also have some other metals. So, we will discuss how to remove those, and sulfur can also be present in this case as inorganic sulfur and organic sulfur. So, we will discuss how the sulfurs can be removed. So, this sulfur removal process is called sweetening process, sweetening of the liquid fuel, and it is most important for the refiners to improve the quality of the liquid products, and this is done by alkali extractions and hydro treatment. The impurities removal are very important because it helps to improve the quality of the product. Now, we will see in which form sulfur is present in crude oil. So, it can be in inorganic form or maybe in organic form. So, organic form basic compound is thiols RSH. So, alcohols are OH. So, this O is replaced by sulfur, then it is called thiols and mercaptans. So, this is the major compounds present in petroleum crude, and then sulfides may be RSR. So, this two alkyl groups with sulfur that can also be available, or disulfides RSSR, and maybe cyclic sulfides as shown here, and then thiophene and benzothiopene. Some benzene ring can also be available with the thiophene, and then dibenzothiopene, this is the structure, and naphthanobenzothiopene. So, these are the molecular structure of these compounds which are present normally in petroleum crude. And if we think about the nitrogenous compound, so those are some non-basic type and some basic type. So, non-basic are pyrrole, this is C4H5N and this is the structure, and indole C8H7N, this is the structure, carbazole and benzocarbazole, then it may have basic type, that is pyridine, quinoline, and then indolene and benzoquinone. So, benzoquinolone. So, these are some compounds. Now, we will see how these compounds can be removed. We will discuss first how the sulfur can be removed, and for the removal of sulfur compounds number of methods have been reported and used. So, those are caustic wash, then doctor treatment, then copper sweetening and Mirox process, which was the advanced one. So, we will discuss about all these processes. So, if we want to remove the sulfur and if it is present is sulphide, so sulphide is acidic in nature. So, if we use alkali solution, so that sulphides or H2S will be dissolved in this NaOH solution, and if we use this alkali solution, that is caustic lye. So, that caustic lye and crude oil or any other liquid oil we will be mixing well, and then there will be two layer, one aqueous layer and another is your organic layer, that is oil layer. So, that oil, all the impurities like sulfur, mercaptans and sulphides will come to the lye solution, and the reactions is represented here RSH plus NaOH, that will give us NaSr plus H2O. So, this is the conversion which takes place during this process, and the mercaptans are made free from the sulfur. So, sulfur removal takes place like this way, and then it will come to liquid phase, and that sulfur recovery and lye recovery can take place. Now, this process we use the lye solution of lower concentration, not high sodium hydroxide concentration, where it is 5 to 20% weight by weight are used at 20 to 45 degree centigrade and 5 to 40 psi pressure. If we use the high concentration of NaOH and high temperature, then it will have some drawback, that it may produce some color body as well as the product may lose the stability. That is why this condition is maintained. And when the lye solution we are using, that it is not possible that all the lye or NaOH solution is consumed by sulphides. So, if it is around 65% sodium hydroxide is consumed by the sulphides, then we call it as a spent lye solution. This spent lye solution can be used further for the removal of hydrogen sulphide, light mercaptans, organic acids or mineral acids. A lye solution that is spent as far as hydrogen sulphide is concerned may still be used to remove mineral or organic acids from petroleum products. Now, we will see what is the doctor treatment. So, doctor treatment in this process, mercaptan is removed by the use of sodium plumbite and elemental sulfur. So, the mechanism is like this: this mercaptan will react with sodium plumbite and this PbSr2 will form, and then sodium hydroxide will be formed, and this PbSr2 which is produced here, that will react with sulfur. So, it is react with sulfur and then it will give us RSSR plus PbSXR, X is any number say 2, 3, 4, 5 like this. So, plus 2 PbS, and then PbSR2 also can be oxidized to some extent to produce RSSR plus PbO. So, these are the chemical reactions which takes place for the conversion of mercaptan to these products. Now, this process have some disadvantages, like say we are using excess sulfur. So, if we can make some mistake and more sulfur is added, then that sulfur will produce more polysulfides, which is not desirable in terms of corrosive nature of the fuel. So, it may fail the copper strip corrosion test, and when more sulfur is used, then that PbSR2 will be more, and that can also be converted to PbO. So, that PbO conversion can be more, and more PbO it will create some other problem that we will call water tolerance test. So, that water tolerance will be reduced. So, these are the two major disadvantage of Doppler process. Then we will see copper sweetening process. Another process which was used to remove the mercaptans was the use of copper chloride. So, if we use copper chloride, so mercaptan will react with this copper chloride. So, cupric chloride, so CuSr plus HCl plus RSSR, this is the reaction. And then if we have cuprous chloride, then the reaction will be this. So, CuSr which is produced here, it can again react with CuCl2 and give us RSSR plus 4 CuCl, and then CuSr can also be oxidized to CuO and RSSR. So, this process also have some drawback. So, what will happen in this case? This cuprous mercaptide, that is oil soluble cuprous mercaptide, remains in treated oil, and then copper chloride reacts with naphthenic acid, phenols and other polar compounds to form oil soluble copper compounds. The oil soluble cuprous mercaptide oxidation to copper, this reaction will make this product to fail the water tolerance test. It will prevent the product to pass the water tolerance test. Then we are coming to Madras process. So, Madras process is the advanced one. So, it replaces the previous processes, and in this case we use some catalyst, and this process is developed by UOP in the year 1958, and it completely replaced the older processes, and it is very simple with respect to others, and it can be performed by two ways. One is light molecular weight mercaptans from the LPG and light straight run naphtha, those can be separated by using some alkali solution, then that can be catalytically oxidized. So, we have say LPG or straight run naphtha, So, this we will be reacting with some alkali solution, and it will give us the mercaptans will come here in the solution, alkali solution, and then this solution will go for catalytic oxidation. So, this is the mechanism through which we can do, or directly we can also handle high molecular weight mercaptans present in heavy naphtha, FCC gasoline, ATF, kerosene etc. into disulfide. So, this is the two way of processes for two different type of feedstock, and the basic reactions are here RSH plus NaOH. So, oil phase plus aqueous phase, it is giving us NaSR plus H2O, and then NaSR produced here, that will be oxidized, and then 2H2O, NaOH plus RSSR. Again oil phase we are getting insoluble in caustic. So, this is insoluble in caustic and we will be getting it. and separate it. So, RSH plus O2 2RSSR plus 2H2O. So, these are the reactions which take place in this Maddox process for mercaptan removal. Now, this reaction 1, this is very mostly applicable for low molecular weight mercaptans and at low temperature and high caustic concentration. Now, we will see how the Maddox process work. So, this we are putting here feed, then we need one caustic pre-wash. So, then after washing some mercaptan is going out. So, rest is coming here and here extractor we are giving sufficient time. This place basically inorganic sulfides are removed and then it is coming the mercaptan removal here in this extractor, and then the mercaptan rich alkali solution is coming here and is going to second step for air addition, and this is our oxidizer catalyst are used. Then disulfide forms here. So, disulfide is coming and here it is separated. So, disulfide separation, spent air is going out and then disulfide we are having here two phase, disulfide phase, oil phase, and here aqueous phase. Aqueous phase your alkali phase and oil phase. So, this is insoluble in water. So, or alkali solution. So, we are getting the disulfide oil and the aqueous layer containing alkali, it is recycled back to this column extractor for further extraction, and which goes here, that is coming to caustic settler and then sand filter and then treated product. Basically, if it is a LPG stream, if feed is the LPG stream, then that will be gas will come here and we will pass it through the sand filter. So, other impurities if something here, so that will be removed and gas will go here. So, this is a flow sheet for the Maddox process with reference to LPG. Then in this process we see one is your caustic pre-wash, another is your oxidizer, these two very important steps apart from this extractor. So, what we do in pre-wash, our objective is to remove the inorganic sulfides just I have mentioned. So, H2S plus NaOH it will form Na2S plus 2H2O and Na2S plus H2S 2NaSH. So, this type of reaction takes place in the caustic pre-wash, and in the oxidizer which is happening, Na2S which is available in the caustic solution, then it will come in the oxidizer, it will react with oxygen and then Na2H2O3 will form, and this will be NaOH. So, regenerated or this alkali solution again we are getting. So, that is recycled, and NaSH will react with 2O2 and Na2H2O3 plus H2O, and again Na2S plus 2O2 plus that gives us Na2SO4. So, these are the reactions which take place in oxidizer. Now, in this oxidizer we supply air. So, what will be the air requirement? Obviously, we have to provide excess air than the stoichiometric requirement, and typical value is given here 0.84 normal meter cube per kg of RSH sulfur. This is the stoichiometric requirement, and say excess air 100 to 200% is provided. If we increase the air, then it causes rapid and complete caustic regeneration. But if the air supply is very high, then some disadvantage we may get, that is dissolved oxygen will be more and that can cause sweetening in extractor, because we are recycling this in this, and spent air will have higher oxygen leading to increased corrosion and hazards. So, that is the one important drawback if we use very high oxygen here or air here, and settling of catalyst may also take place. Now, how can we quantify the air requirement? There are some formula, it is provided here in case of LPG. So, air requirement is 1.5 into 0.84 into F into Sg into RSH by 1000. So, air injection rate is normal meter cube per hour, F is the LPG flow rate meter cube per hour, and Sg specific gravity of LPG at 15.5 degree centigrade, and RSH is the mercaptan sulfur in ppm weight basis. So, now this oxidizer or oxidation unit of Madras process is a catalytic process, and UOP have developed two catalysts, one is Madras WS and another is Madras FB. So, Madras WS is a totally water soluble and specially formulated catalyst for use in extractive or liquid sweetening. So, it is a liquid process, liquid solution. In this form the catalyst is available and specific gravity 1.16 plus minus 0.01 and freezing point 0 degree centigrade. Active ingredient is 1 kg per gallon. Now, for Madras FB catalyst, this is developed for in situ impregnation of the fixed bed sweetening version of the UOP Madras process. So, some fixed bed is used in this case, and Madras catalyst is impregnated on it. It is as water slurry ready for use in the fixed bed Madras reactor impregnation step. So, this is two type of catalyst they have developed on application point of view, and here it is also liquid dispersion, specific gravity 1.15 plus minus 0.01 and freezing point 0 degree centigrade, and active ingredient 2.5 kg per 2.5 gallon. Now, examples of applications of the Madras process. So, different type of feedstock we can use, different types of feedstock can be cleaned through this process, and these are the applicable treatment. So, how what the people have done for different type of feedstock, so what type of options of the Madras process have been implemented is provided here. So, if it is LPG, mostly extraction based process, and then light straight run naphtha, extraction and liquid sweetening, breaker gasoline, fixed bed sweetening, and FCC gasoline fixed bed, and then full boiling range straight run naphtha, liquid sweetening, fixed bed sweetening, and both can be used, and then kerosene, aviation turbine fuel by getting fixed bed sweetening. So, these are the preferred configurations of Madras process for different type of feedstock. Now, we will discuss the hydro treatment, how the hydrogen is used to remove the impurities. So, in terms of hydro treatment, we can term it as hydro processing. So, this hydro processing is thermal conversion process in which hydrogen is used to accomplish the objectives of the refiner. So, this hydro processing can be of two types, one is hydro treating and another hydro cracking. So, hydro treating means we provide hydrogen under such conditions for a certain duration that only sulfur and nitrogen, those compounds will be separated from this. So, this is the process in which hydrogen is used to convert heteroatom constituents into their heteroatom hydrogen analogues and hydrocarbons. So, this is RSR1 plus H2. So, RHR1H plus H2S. So, that this S is removed by hydrogen to produce H2S. So, only sulfur is removed. There is no cracking or molecular change in this compound, and hydrocracking is a thermal decomposition is extensive and hydrogen assists in the removal of the heteroatoms as well as mitigating the coke formation which normally accompanies thermal cracking of high molecular weight polar constituents. So, if we go for thermal cracking, then what happens, there is a coke formations on the catalyst, but if we use hydrocracking, so that coke formation will be reduced because those will be converted by this addition of hydrogen. So, coke will not be deposited. So, that is called it is hydrocracking. So, hydrocracking will reduce, will break the bigger molecules and it will convert it into lower hydrocarbons rather than deposition of coke, unlike thermal cracking process. So, major differences between hydro treating and hydrocracking are the time at which the feedstock remains at reaction temperature and the extent of decompositions of non-hetero constituent and products. How long we are providing this feedstock in contact with hydrogen and what is the condition of the reactor. So, those will differentiate this low less. Okay. So, now we will see the comparison of these two processes, and before that we will see the reactions mechanism which take place during hydrotreatment or hydroprocessing. So, sulfur compound, when hydrogen is added, RSH is converted to RH plus H2S, and then RSR plus 2S2 2RH plus H2S, RSSR plus 3H2 2RH plus 2H2, and H2S it combusted to CO2 and SO2. So, these are the reactions which take place during the hydroprocessing or hydrotreatment of the feedstock. And then for nitrogen removal, when we add hydrogen, the nitrogen is also removed, and this is the mechanism. We have one hydrogen containing compound. So, that is we are using some catalyst and H2. This catalyst is basically, so acid base pair plus H2, that converts this one to this moiety, and there are two reaction steps, two routes, that is 1 and another is 2. So, this intermediate products forms in this route, and that is converted to this one, and again finally converted to this product, and we get ultimately this one typical presentation of this phenomena. Another route we get this intermediate product. So, here it is coming to this one almost similar. So, substitution 1 and 2 reactions, and then it is converting to this one. So, ultimately this way nitrogen is removed from the compound. Now, substitution reaction leading to denitrogenation, this was our compound. So, H2S is present. So, this N will be replaced by S, that can also be possible by the ammonia release. So, these are different type of reactions which may take place during denitrification process, denitrogenation process, and here the catalyst which are used, those catalysts are basically tungsten and molybdenum sulfides on alumina, supported on alumina, and their properties are modified by adding some cobalt and nickel. So, those are because of hydrogenation promoters. So, cobalt and nickel. So, cobalt molybdenum and nickel molybdenum, two active ingredients we are getting for the nitrogen sulfur and nitrogen removal. So, out of these two, this one CO molybdenum is less active than nickel molybdenum for nitrogen removal, because nickel molybdenum catalysts have higher hydrogenation activity than cobalt molybdenum catalysts. Now, we will see the metal removal, how the metal can be removed from the product or the feedstock. So, as you have seen that in the crude oil different types of metals are available. Some metals are available in water, in emulsified water, there is calcium, magnesium, sodium, etc., and some metals are also there, that is vanadium, nickel, tin, lead, cobalt, titanium, gold, etc. Those are in less amount, and typically vanadium and nickel, those are mostly available in crude, and the concentrations are vanadium varies from 0.1 to as high as 1200 ppm, and nickel commonly varies from trace to 150 ppm. So, nickel and vanadium, these are two major metals are present in the petroleum crude, and which needs removal from it to get high quality liquid product. In which form this vanadium and nickel exist, there are two thoughts. One is told that is your porphyrynic, and another is your non porphyrynic. So, porphyrynic state or non porphyrynic state, in which form they are existing. So, most of the literature prefers the porphyrynic state, and more information is available on this. Other one is not widely reported, and this maybe the molecular weight of this type of compounds 420 to 520 and molecular formula is C27N4 to C33N4. So, this is the representation of this porphyritic metallic compounds. So, we have to remove this metal. So, for the removal of this metal different types of methods are applied, physical and chemical methods. So, physical methods basically solvent extraction. So, we add some solvent. So, lighter parts from the vacuum residue it comes to the solvent and heavy asphaltenes etc., where the porphyritic compounds those go at the bottom. So, it is separated from the oil. So, that way it can be done, or thermal process also used, that is the visbreaking etc. And the chemical concept of demetallization is selectively remove the metal from the organic moiety with minimal conversion of the remaining petroleum. The demetallization of metalloporphyrins by acid a reversible reaction. So, this is the reactions it is shown that PM plus HX porphyritic metal and acid HX. So, that H may react with metal chloride we can get, and that will be the compound porphyritic compound without metals. So, that way the addition of acid can convert the metal into their salt, respective salt. So, then catalytic hydroprocessing, these are the chemical and physical methods. Apart from this we can go for hydroprocessing steps using some catalyst. In that way also these metals can be removed along with nitrogen, sulfur and oxygen. So, these are the different routes through which the metals, sulfur and nitrogen are removed from the liquid oil to make it more cleaner transport fuel. So, thank you very much for your patience.